Physics students, good afternoon, Mr. Fugit here. In this video today, we're going to be looking at something we've been studying in class over the past couple of weeks, what we've called the Work-Energy Theorem, the relationship to work being done, which transfers energy either into or out of a system, and how that affects the energy of that system. Excuse me. Specific to this problem, we're going to be looking at problem number 4 from your homework assignment, which covers over work and energy. Okay? So this problem involves an object being pulled that also is encountering friction as well. So the problem statement says this: a team of dogs drags a 103 kilogram sled 1.73 kilometers over a horizontal surface at a constant speed. The coefficient of friction between the sled and the snow is 0.18. The acceleration of gravity is 9.8 meters per second squared. Find the work done by the dogs. So, there's a lot of information wrapped up in this problem, but one thing that can be very helpful in solving this is first to start by kind of putting together a picture. Now, to keep things simple, effectively we have an object that's being pulled, we're told, I believe, on a horizontal surface, so just, we'll say flat ground. Here's our, let's say, our object, the sled, if you will. We won't get too fancy. And we're told the sled is being pulled by a pack of dogs. So let's just say it's being pulled out some direction. Okay? We're also told that there's some friction between the sled and the ground. Okay? Okay? We typically describe friction as a resisting force. So as the dogs pull, friction is going to work against that pull. Okay. Now we're asked, well, some things we're given. We're told that the dogs are going to pull the sled a distance, we'll say delta x, of 1.73 kilometers. And as you go about solving your problem, the numbers are going to look a little bit different, but the process will remain the same. We're also told the coefficient of friction between the sled and the snow is 0.18. I pause as if there would be a unit there, but there's not. My apologies. And so we're asked to find the work done by the dogs. Now, typically, when we're dealing with work, there are two ways we can go about calculating work. One, we can use just the work equation, force times displacement times cosine of the angle between those two vectors. Or we can say work done is equal to a change in energy. Now, right off the bat, what I notice is that we're given a delta x, how far the dogs are pulling the sled. So that should tell me that I might use my work equation, force, displacement, cosine of the angle between them, because I'm already given one piece. I'm also given this coefficient of friction, which might help me kind of figure out what's going on with some forces here. Okay? So, to kind of describe, or to kind of figure out what we need, let's say we want to go with this approach right here. Okay? Work is force, delta x, or displacement, cosine of the angle between them. Okay? So what I'm going to do is, I'm not really going to use our approach for change in energy here. Not that we absolutely couldn't, but I'm just going to choose to use this approach. So find the work done by the dogs. Well, to find that work, we need to find the amount of force that they're applying to the sled, which is going to be tricky because we're not really given any numbers here to describe that. But there's a phrase here that's very important. We're told that we're moving at a constant speed. So here's what that means. If we're moving at a constant speed, what that tells us is that we don't have any acceleration. So sum of forces in the x direction is equal to mass times acceleration. Well, this is going to 0, because no matter what our mass is, which we're also not told, we don't have any acceleration. Remember, acceleration is a change in velocity. So what that means is that the amount of force I pull on with the dogs, or the amount of force the dogs pull, is also the same amount of force that friction is pulling with. Now that doesn't mean we're not moving, it just means we're not accelerating, right? Our velocity isn't changing. So those two forces are going to be equal. So that's an important relationship. Our pull force is going to be equal to our force of friction. Now I'm going to take that and I'm going to come to a new page and then we're going to come back here. So we have our pull force, Fp, which is equal to our force of friction. Now on the box, we just momentarily looked at what was going on in the x direction. But, we'll remember, frictional force is related to the contact between two objects, or two surfaces. Here the sled and the snow underneath it. So our frictional force is equal to our coefficient of kinetic friction times our normal force. Now remember, the normal force is a contact force. It always runs perpendicular to our contact surface. And also in the y direction, we have gravity acting to pull our object down toward the ground. So what we can also kind of assume about this problem is that we're being pulled across a horizontal surface, so we're not moving at all vertically. And because of that, that tells us our normal force and our force of gravity also have to be equal in magnitude. So sum of forces in the y is equal to mass times acceleration. This is going to go to 0, right? Because we don't have any acceleration, we're not moving vertically. So that tells us our normal force is equal to our force of gravity, which we know is just mass times gravity, mg. So, we're given some information, but we also have to work to kind of figure out some of the information that we're not directly told. So I'm going to use this relationship to plug in here. So, first things first, let's take our calculator. We're going to take our mass, which for me was given to be 103 kilograms. That's from the problem statement, times g for the Earth, 9.81 meters per second squared. So that gives me a normal force, 9.81 times 103, right at about 1,010 newtons. I'm going to take that, I'm going to plug it in to find my frictional force. So I'll take frictional force, Fk, is equal to our coefficient, which we were given directly, 0.18, times the normal force, 1,010 newtons. So I'll take that value, multiply them together, and I'm going to get a value for my frictional force. Looks like about 182. This is a force value, so it's going to be measured in newtons. Okay. So this is how we would go through and find the force that we'll need to plug into our work equation. Force times displacement, cosine of the angle between them. Okay, so I'm going to take that 182 newtons, I'm going to write it in here. My pull force, which remember is equal to my frictional force, what we solved for earlier, 182 newtons. Okay, so if you'll notice now we have two of the main pieces that we'll need to find the work that's being done. We don't have the angle between them, but here's what we can tell. Okay? We're going to be, or the dogs are going to be, we should say, pulling our sled. And we're going to be pulling the same direction that we want the sled to be moving, right? So because we're going to apply a force in the same direction as our displacement, our angle between those two, the force and the displacement, well, there's really no angle between them there. Okay? So cosine of 0 is actually going to give us a value of 1. So, and we're going to take all the values that we have now, our force, the displacement, and we're going to plug those in. But, before we do, don't forget, and we're always going to plug that value for a delta x in units of meters. So I'm going to multiply this by 1,000, 1,730 meters. Okay? Right, just so that we make sure when we get a unit for joule, remember a joule is a newton times a meter. So we have to make sure that we pay attention to that unit. So let's go ahead and take the values that we have, and solve for the work. Work is equal to our force, apply, 182 newtons, times its displacement, how far the force is applied over, 1,730 meters, and cosine of 0 is just 1. So we'll take our value, force times displacement, and I get a value for the work done. That's pretty large, 314,000. Well, 647.9 newtons times meters. That gives me joules. There's my amount of work done. Which again is going to seem like a lot of work compared to some of the scenarios that we've dealt with. But remember here, we're applying a very large amount of force over a pretty significant distance. So it's going to take a lot of work in order to get that done. If I look at my key, I'm given what looks like 314.3 or 0.6 kilojoules. Kilojoule would just be this value, joules, divided by 1,000. So 314.6 kilojoules. So just make sure we're paying attention to what units the actual homework system is wanting us to submit in. A kilojoule is the same thing as a gram to a kilogram. Just a way of representing that unit a little bit differently. So hopefully this will get you started kind of working through this style of problem. This is a great example of where we see something like forces and Newton's laws being related back to what we're covering now with work and energy. Best of luck.